and welcome to Chapter 3. In Chapter 3, we're going to start going over the relational database model. Like, we're going to be talking about different parts of it, how we build it, and the things that we put in it. Let's get started. So the basis of all of the modeling that we're going to be doing is just basic logic. We're going to take predicate logic, which is simply statements that can be determined to be true or false. So we're going to determine whether or not something is true or false and use that logic when we build our database model. We're also going to use some higher order math concepts called set theory. Set theory deals with sets and groups, and it helps you to understand the data manipulation that we're going to be doing. Understanding what happens when you run an update query on an entire set. It's going to update all of it, or is it going to update a portion of it? How that set theory works when you're working with a set of data. If any of you have taken a higher order math class, you might have heard that word, set theory. So we're going to use some of that logic in our database design. And finally, of course, is the relational model itself. Viewing the data logically, not physically. So for the purposes of this, we're not thinking, how are we actually building our database in reality? What we really want to get here is the conceptual view. What do we want our logic to look like in our relational model? This is where we are going to have those many-to-many relationships without putting that helper table in the middle. So these are the three different parts of logic that we're going to be representing in our models. The first basic question we're going to ask is, so what is a table? I know it seems redundant and silly, and obviously you know what a table is. However, I do want to get into the basic characteristics of a table so that you can really understand all of the things that are included. A table is simply a two-dimensional structure with rows and columns. Okay, that's pretty easy. We've understood two-dimensional arrays probably in a previous computing class. We've done matrices in our math classes. We understand what a table is because we've used Excel, we've used spreadsheets. So we understand the basis of a table. When we refer to the individual rows, we call them records, a record in a table, and we call it a tuple because it has multiple attributes in it. It can have 1 or 2 or 5 or 20 or 50 attributes in each row. So we just call those a tuple because we don't know how many, and tables can have multiple values. So we keep in track of that when we're doing our data modeling to make sure we understand how many different fields we're dealing with. We might call them attributes, we might call them field names, we might call them column names, a lot of different ways to refer to them, as long as you understand what they mean. That's the important part. Basic characteristics of a table, relational table. So table has rows and columns. That's easy. Each row has a tuple that represents a single entity occurrence within the entity set. So you wouldn't want to have some data in row 1 and some data in row 2. All of the data related to the record is going to all be in one row. Each table column represents an attribute. Okay. And each column has a distinct name. Understanding that there is a name that goes to that, kind of like a variable name. You know how you can't have two different variables with the same name because everything gets confused? You can't have two different columns with the same name either in the same table. You can have two column names that are the same in two different tables. That's fine. But when referencing a single table, all of the different column names have to be distinct. They have to be different. Each intersection of a row and a column represents a single data value. Okay, this is where a lot of people kind of can mess up in their database design. If you remember back to chapter 1 or chapter 2, I think it was chapter 1, where in the homework assignment they had address, city, state, zip, all in the same attribute field, all in the same table, or the same column. You want to try to only hold one piece of data per cell. So I call a cell the intersection between a row and a column. So each cell or each data field only holds one piece of information. That will make it so much easier to pull your data back out because you can pull out multiple columns, but pulling out a singular column and then trying to parse through it is just a pain. All values in a column must conform to the same data format. This is important. If you have a date in a column, all of the data fields in the column must be a date. If you have a string, they must all be strings. If you have a limitation on how long those strings are, they must conform to that limitation. If they have number fields, they all must be numbers. They all have to be the same data format. You have to have the same data type. Each column has a specific range of values known as the attribute domain. if you can only have certain values, say your ID field has to be a 4-digit number or less, then the range could go from 1000, because it has to be a 4-digit number, or 0001 if you're going to allow zeros that way, up to 9999. So it has a range. We call that the attribute domain because these are the possible values for this attribute. And it's important when you're designing your database rules, understanding those constraints and putting those into your ERD so that it's obvious to everybody else around. The order of the rows and columns is immaterial to the DBMS. It doesn't matter if you put your primary key first, and it doesn't matter if you have your first name first and last name second, and address third, and city, state, zip fourth, fifth, and sixth. However, when you look at the table, it's kind of useful. There are some situations that you're going to find in the real world where you've created a table and you want to add a field to it at the end, but somebody else has already referenced that table and has just used select star instead of selecting the individual field names. You adding that extra column at the end is going to break their code. Yes, this has actually happened. So you need to be careful about how you add fields to your table if you're going to add them after the fact. When we create a table in the database, you use a create statement, you build your table. You can add to those or remove them as time goes on. It's not recommended, but you can if you have to. But the order is not really material. It doesn't really matter to the DBMS which fields you put where. If you order them in one way or the other, it doesn't matter. And each table must have an attribute or a combination of attributes that uniquely identifies each row. This is a big one, and we're going to get into primary keys in about 3 slides. But this is the combination of attributes that make up your key, that uniquely identifies, that will not be duplicated. If you think about it, sometimes if I wanted to say first name and last name is my key because those are going to be unique, and I'm going to have 2 John Does, then I'm going to have 2 rows that are John Doe. And if that's my unique key, how do I compare that to other tables? Which John Doe did I really want? The way to solve this is you add in a primary key that's an ID field or something like that, and that's now your primary key, whereas that first name and last name are not. So you want to make sure that in your table you always have something that uniquely identifies each row. It is unique to each row so that you can reference against it when you're going to do your queries. Just a quick little note, if you have done object-oriented programming, Java, anything like that, C#, actually we do classes in Python, so yeah, anything with a class. You can think of it as table is an array of students, and each student has data fields of student number, student name, so on and so forth for the student table. So you can just think of it as each row is an individual object or instance of an object, whereas the table is the array of all of the objects that you've created, if that helps at all. So when we create data tables, we're going to create a series of fields in them. These are our data attributes or data fields that each table is going to be consisted of. Your data attributes must have a distinct name. So you can't have the same name for 2 different columns. That doesn't make any sense. When we write things in databases, we give them a data type because the database needs to know how much space to allocate for each data field when it creates the tables. So everything has to be the same data type because it's a different allocation for a date time than it is for a string, than it is for a number, than it is for a Boolean or an identifier field. So these are different data types that you're going to have. Databases are strongly typed, just like strongly typed languages like Java or C, where you have to have a specific type for each variable. In this case, you have to have a specific type for each data field. And again, each data type, each data field is going to represent a single attribute. You want to try to avoid multiple attributes, multiple pieces of information in the same data field, kind of like the way we did the address, city, state, zip, all in the same field. You want to try to avoid that because you want to only have a single piece of information into each data field. It allows querying much easier. When we use data fields, there is a set of data options, data type or a valid data options, which is your domain. So if you remember domain and range, again, back to high school math, Your domain is going to be the possible list of options that you could put into this field. So if this is a date field and it's an age, for instance, then your possible options are probably 1900 through 2020, because people aren't going to be more than 120 years old unless you're representing an age for a different purpose, like a ancestry type situation. But you probably have some semblance of a domain or a grouping of options for this data field. If we had a GPA, I might say 0 to 4.0. So those are just limitations that you would have in your constraints in your business rules to describe your possible data options. When we create our fields, the order is not really important. Your query will pull out the data fields in a given order, depending on how you write your query. And then the user will probably manipulate that as well on their side with your application. So you don't really have to worry about ordering. That being said, remember, if you're working on a legacy project, one that's already been implemented and in use, and then you're modifying it, there may be code where a user has said select star from table students, and they expect 15 columns because those are the 15 columns that were there when they wrote it. If you decide to add a 16th column, their select star and then plugging it into their data type for their object in their application may break. So you need to be very, very careful about adding or removing columns from your table, especially in a legacy table, because things like this can occur. While you're first building, you're going to probably realize, oh, I forgot to add this data field, and you'll go ahead and add it in. And that's usually fine at the beginning, but as your code gets longer and as your database gets larger, it's going to be harder and harder for you to be able to do that without breaking something. Finally, tables always have a primary key. So a primary key is a unique identifier that will describe each row or each record in your table. I like to use identifiers. I like to use primary or GUIDs, which is an identifier. It's a created number for my identifiers because I can be guaranteed that they are unique. There is no possible way I'm going to add this twice. Some people will start with like record 1 and then have it increment. So some DBMSs will allow you to do an auto increment. Start with 1 and it'll automatically increment every time you add. You can't always guarantee that those are not going to remove data fields or remove records or add records later, so you may not be able to be consistent with your numbering, but it also usually works because you probably won't end up with duplicate records if you just use an auto increment. But a primary key is simply a unique data field. It can be a collection of fields, which we'll talk about when we get into keys. But we use it when we do indexing or protecting it from data redundancy. So when we do indexing, it allows your queries to run faster because the computer will have run through and come up with an index of all of those primary keys. If you can do joins on primary keys, it's a lot faster than not. We'll get into that with joins. Let's keep going. All right, so now we get to talk about keys. There are different types of keys that we're going to be talking about. The primary key, the one you're going to use the most often, is just one of the types of keys that we're going to be using. These are also really well described in the book as well. So if I do kind of lose you on this slide, go back to the book, read the section in the book, and maybe make yourself a chart of the different keys and what they kind of are, how to describe them. When we make a key, we're going to use determination, which is simply knowing the value of one attribute, which will determine the other attributes. If I tell you my key is 6, you can then go into the database and say, where is key 6? Oh, it's this record. And I can get all the other attributes that go along with it. The purpose of keys is to be able to do that. So any type of key that we're going to use is going to allow us to determine other pieces of information because we know that key. It's kind of how a key works. If you know the key, you can get the information out. If I know that the speed and time, I can determine my distance. So in this case, speed and time would be your keys. They would be the pieces of information you need to be able to determine your distance. In databases, key or determination is based on the relationships. So when we have a relationship between two tables, we need to have a way to say how are these two tables related and what piece of unique information, key, is going to be used to determine that. The determinant is the value that determines the other values, which is dependent. So the other values are the dependent. The determinant is the thing that determines it, which is a key. Again, just vocabulary. A primary key, again, most important one you're going to have, is usually a single value that is unique to the table, and it cannot be null. Null is just no value. We're going to talk about optional values a little later on. You can't have it be null. It has to be put in there, it has to be entered, and it has to be unique. This is your primary key. If it is your primary key, by knowing that piece of information, I can determine the rest of the information in that record. There's also the concept of composite keys. You can have a composite primary key. Composite key is multiple values that combined to determine the other attributes. They're a way of making a primary key made up of two different fields. So if I said I wanted to have the student number and the last name be the primary key, I could make that a composite key. So it's now two fields instead of one field. So composite keys. If I wanted to make the key be the first name, the last name, the initial, and the phone number, because the odds of all four of those things being the same for any one user is pretty slim. So any one student is never going to have the first name, last name, middle initial, and their phone number all be the same. Even if they had the same first, last, and middle initial, they probably live at different addresses. So they probably have different phone numbers. Probably. Unless somebody entered the data twice, which is where you get into that data redundancy. The point of keys in a lot of ways is to prevent that data redundancy, to prevent you from accidentally entering the same person twice. So composite keys are simply multiple values that make a key, as opposed to a primary key, which is usually a single key. A super key, because we didn't have enough other keys, let's talk about super keys. Super keys are keys that can uniquely identify any row. Usually it's also the primary key. However, you can have a super key that is not your primary key. So my social security number could be a super key. I probably have an ID number somewhere in the database, but if I've entered my SSN, it's probably pretty unique, and I should be able to use my SSN to run queries if I needed to be able to get my records out. So an SSN, for example, is a super key. It's a key that can be used, that is unique, that can be used to identify any row. The last one on this slide is a candidate key. It is a minimal super key with no other unnecessary attributes. These are the ones that we use. They are candidates to be our primary key. Most tables only have a singular primary key. You only have one thing that you say, this is my primary key. However, you can go through and say, these are all the super keys I have. So I could put things like first name, last name, date of birth, as a combination. The odds of somebody having the same first and last name and the same birth date, pretty slim. My social security number could be a candidate. My student ID number could be a candidate. These could all be candidates. And then once they're a candidate, now I can go through and pick which one of my candidates is going to actually be the primary key I'm going to use. Being able to identify your candidates is really useful, because you may not need a unique identifier if you have a candidate that will work just as well. Just keep it in mind. I still like to add a unique identifier because I find that it's easier. But when you do your design, you may find you don't need to. You can use one of your other candidates and you don't need to make one. So candidate keys are simply candidates for primary key. They're all challenging to see who gets to be the primary key first. And that's a way that when you're designing your database, you can have that to look at and go, which one of these do we want as our primary key, instead of just automatically going for it. Okay. You thought you were done with keys. No. So we have other keys. The foreign keys are actually really, really important. Foreign keys are a primary key from a relationship table that is in a secondary table. So if I had my enrollment for my students and I would have the student ID as a foreign key in my enrollment, student can be added multiple times, so that's not unique. I can have a lot of enrollments, but that's a foreign key because it's a primary key in another table. It's used as a data field. We use it for referential integrity to make sure that if every reference is either valid or null. If I'm going to enroll, I need to make sure the student exists. So I need to have a primary key from the student table as one of my fields so I know which student I'm referencing. If I don't put that in, or if that's not a foreign key, if I just put in the student's name, I'm not going to be able to have that comparison, that attachment between the two. So I need to have a foreign key in my table to do the connection. In the example here with the product and the vendor code, our vendor code table lists out all of our vendors, so the vendor names, and then every product has to have a vendor code. That vendor code is going to be able to link back to the vendor table from our products to be able to give us what the vendor information is. We also have what we call secondary keys. They're not primary keys, but they can still be used to look up values. So if you think of, I have a primary key, say at the school, you have your student ID, but sometimes you don't know your student ID. So maybe I could go by my net ID. Sometimes I don't know that either. Well, I could also look it up by my social security number. Yeah, can't remember that. Okay, we can look it up by first and last name. We can look it up by date of birth. These again can be secondary keys. So last name, phone number, date of birth, email address, to be able to return values. They might accidentally return multiple values, but that might be okay. Because for the purposes of the application, if I'm doing a quick search on all of the students, that were born in January, that's something I might use to look up something. If I'm looking up, you come in and you ask me to find your records, and I might look it up by your first name, because the odds of me having multiple students with the same first name, kind of slim, possible, but I might only get 2 or 3 records as opposed to my entire class list. So secondary keys are very useful. A quick note on null. Null is simply the absence of data. Do not compare null against spaces or zeros. It's not zero and it's not a space. It is an absence of any data at all. Some functionality will fail if you use nulls. So if I have a count or an average or a sum that I want to do some math on my data fields, and I have a null value in there, it might make problems for you because it's not going to count correctly. There's no data value there. Null is simply the absence of data. So don't get that confused with zero or a blank space. A quick word on integrity rules. So there are 2 different types of integrity rules we're going to talk about for this slide. Entity integrity and referential integrity. So an entity is the table itself. So think of it as it is guaranteeing that the table is good. It has integrity. It's going to do exactly what it's supposed to do, and it's not going to break. To have entity integrity, you must ensure that your primary key is unique and not null. Very important. You cannot have a null primary key. So to do that, we ensure that any record that exists in this table is going to have a primary key, and that's going to be a unique primary key. There are not going to be any duplicates, and there's not going to be any blank spots. There's not going to be any nulls, which is really, really important for the purposes of comparisons and joining later on. Referential integrity is where the referring tables are related, and we're talking about foreign keys. Remember, a foreign key is a field that exists in a table that references back to another table's primary key. We are guaranteeing that our foreign keys will either be null or will be a valid primary key. One of the things that happens a lot in databases, if you don't design it correctly and you don't put in the right code. I have a client, and the client has a customer rep. So there's a rep that's associated with the client, and that's fine. So we have the database with the client, and then he has a foreign key that's related to the rep John Doe over in the representatives table. Cool. And then John Doe quits. So John Doe quits, and there is a reference to John Doe's ID number sitting in my client's table that says, in my client table, John Doe's ID 1, 2, 3, 4, 5 is his representative. But there is no 1, 2, 3, 4, 5 left in the representative table because John Doe quit and we deleted his record. That would be a break in referential integrity because right now that record, that foreign key, is referring to an invalid rep ID. So making sure in your code that when you have a foreign key that is attached to another table, if you allow deletes on the other table, make sure that you, in a way, and we'll talk about triggers and ways of handling this, make sure that you recognize that could be a problem and recognize how you could fix it and trying to do everything you can to make sure it doesn't happen. So the example that they give you here is that a customer might not yet have been assigned a sales rep. You can have a null. Null is okay in this case. Your foreign key can be a null. That simply means there's no value there. There's no person that's representing you at that point. And that's fine. You can have a null. You just don't want to have an invalid number. That's your referential integrity as far as foreign keys. Making sure that when you have a foreign key, you either will have a valid number or you will have a null, which says it just hasn't been assigned yet. Okay, so now we're going to talk a little bit about relational algebra. These are the actual commands that you're going to be using in your queries to allow you to do certain things with your tables. First, we talk about our relational variable, or relvar. This is the container that's going to hold the reference to the relationship, not the actual relationship itself, but just the reference to it, so that we can use it. And in our relational variable, we can include the header and the body, and there's a little bit more detail in that in the book. Again, terminology, relational variable, relvar, holds the relation. In this case, the idea being that it's just holding a reference to the table or a record set of data. Okay. Relational set operators use the concept of closure. And in this situation, if you've had advanced math classes, you've heard about closure. The use of relational algebra operators to produce new relations. So we are able to use our relational algebra to create new data sets. So if you think of it as I have a table, so I have a data set of records, and I'm going to use my relational algebra to create a new record set that is going to include some or all of the records that are in the first table. And I've made a second table. So we have the concept of closure. Again, terminology. When you read the book, it might be useful for you to write down some of these words and just kind of keep them, especially just for the purposes of being able to know what the words mean. Okay, let's start going through our operations. So these are relational set operators that we're going to be using, and there's the majority of your queries are going to use select queries, but I do want you to understand what occurs in a select query and how the rest of the relational algebra works. We're going to be doing, so first and foremost, a select query. And since we've already done 7.1, you've already written select queries. But a select query restricts the query. So it limits and yields all the value that meet a certain criteria. When we do our select queries for this week, you're going to start adding things into it from just the select and from clause. You're going to be adding other clauses. So a select simply takes data from a database and it limits it down or restricts it to the values from the table that meet a certain criteria. That's all it does at this point. It's just getting data out, which is why you use the select most often. It's the one that gets data out of your database. To project is simply taking all the values for selected attributes and returns those from a table. So when we do a select, we kind of do a select and a project at the same time. We're going to take our data and we're going to get all of those values and then we're going to return them. So the select is getting all the values, the project is returning the values. You do not have to call project directly. It's already done for you. But you need to understand that that's actually what the database is doing. A union. So again, if you've done any set theory, these concepts will be familiar to you. If you have not done any set theory, these may be new. A union combines all of the rows from two tables, excluding duplicate rows, but the tables must have the same attributes. So if I have a table that holds a student ID, a student name, first name and student last name, and then I have a second one. So the first is all of the students in fall semester. And then I have a second table that is student ID, student first name, student last name of all the students in the spring semester. and I want to find out all the students who were in the school for one of those 2 semesters. They could have been in both because we like to exclude duplicates. But we're going to take those and we're going to union them together. So you can kind of visualize that Venn diagram of all of them in first table, all of them in the second table. The ones in the middle only get counted once because we exclude our duplicates. And it'll union those together. It's joining both tables together at the same time to create a third table that includes all of the records in both. That's a union. An intersection, again with our Venn diagrams, it yields only rows that exist in both tables. So you have to have 2 tables to do an intersection. And in this case, it would have the same situation with a union, except instead of doing all of them that are in both tables, it will only do the ones in that middle section where they're duplicates. So if I had all the students enrolled in fall semester and all the students enrolled in spring semester, the intersection of those 2 would be all the students enrolled in both semesters. It wouldn't include any students who were only enrolled in one or the other. Okay, so that gives you the kind of difference between union and intersection. The union in a Venn diagram would be anyone who exists, or like an or concept, in the first table, the second table, or both. And the intersection is kind of like an and. It's the, you have to be in both tables at the same time, and. Okay. Because we like mathematics, we also have the concept of difference. A difference yields all the rows in one table that are not in another table. So if I wanted to find out all of the students that were in fall semester that were not in spring semester, I could do a difference between fall semester and spring semester, and it would have subtracted out all of the students that were in spring semester to leave me with only ones that were in fall but not spring. Again, difference, a subtraction. Okay, product. Product is the possible pairs of rows in 2 tables. It's a Cartesian product. It's a cross product. So it's kind of like the visual of turning the 2 different tables into all the possible options between them. If I had, these are all my, we're over at Subway, and these are all my meat choices, and these are all my vegetable choices. What is the product of possible pairs of meat versus vegetables? So you create a grouping of those. So that's your product, a Cartesian product between 2 tables. Join is the second most important of your relational algebras, because the join allows information to be combined from 2 or more tables. In a lot of ways, I'd like to almost say that the join is more important because it really gets you the power of the relational database, but I can't say that it's more important than a basic select query. Getting the data out is more important. After that is being able to join between 2 tables. So that's where the join comes in. So when we have our foreign key, that's the primary key in the secondary table, I can join those 2 tables together to get a selection of records that will give me all of the information I need without duplication of records in my actual database. We don't like to have that duplication of data because of data redundancies. We don't want to have that problem. So you put your data in the database clean, where there's no data redundancies, and then you use joins to create queries that will get the data out in a way that you can use it nicely. For instance, if I had the example of here is a customer and here is their agent that is associated with their agent, I can attach that agent code with a join to the agent table, and then each row in my record set that is the return value could have the whole customer and all of the important information from the agent, say their phone number or their name, their contact information. I didn't have to have duplicate values in the data because I can use the join to make the resulting record set have duplicate values that are still have integrity. Really important part about joins. We're going to do joins in a little bit. The last one is a division or divide. And you can divide 2 tables. Well, division of tables sounds a little funky. So please go into the book and look at the example of divide. But what it does is it takes 2 columns with the divisor being 1 column, and then it returns records in the second column of the first table in which the first column matches all the values of the divisor. So again, it's a division, which sounds weird, but when you see the example in the book, it'll help. So hopefully that will explain that to you. Okay, so the most important power in a database is being able to join two tables. This is, second only to just getting the data out with a select query. So a join is being able to do a product, which if you think about a product, it's all of the records in both, all the possible rows of both tables, and then a select where we use our on clause to determine where the two fields are equal, and then a project so we can return the result. So a natural join, or the most important join that we're going to do with just the word join, is going to get all the rows from both tables where that on criteria is equal or is met. The syntax that we're going to use is our select star from, okay, so we should be comfortable with that, table A, then we're going to use the keyword join, and table B. So whatever your table names are, you can alias them to A and B, but essentially table name A, table name B. And then we're going to use the keyword on to say A's dot student number is going to be equal to B dot student number. And this will get all of the fields where from both tables where those student numbers are equal. So if you think about what's going on in the background when you do a join, you are going to take all of the records. Say we had a table of students and we had a table of enrollments, and I wanted to get all of the student enrollments and the course code that's coming in, because we have that many-to-many situation. When we do our join, we would say select star from student join enrollment on student dot student number equals enrollment dot student number. And that would give us all of those where the students are equal. The normal join that you're going to do is an equijoin, or essentially an equality join. You're doing the equality operator on that on condition. So it's going to be a student number is equal to another student number. There are other join options like theta join where you can do a comparator with a greater than or less than, using an inequality comparator. You're not going to use these a lot, but they are useful in very specific instances. So you want to keep those in mind. Sometimes we can have joining tables where, or we can have foreign keys where we don't have a value in there. There's a null in there. The system with a regular basic join is only going to return values where that key or that join condition is true, which means any situation where the value that you're looking for is null, those records won't show up at all. So we have the option to fix this with an outer join. What an outer join does is it takes all of the records from one table and only the records from the other table where they have matching values. So we can say select star from A with a left join and then B, and being able to do A student number is equal to B student number, and you will get all of the fields from A and only those fields from B where those matches occur. In the location of those fields in B where there are no matches, you'll just get null values. So it'll just say null in there. The left and right determines which side of the equation you want to have being the one that returns all values. So a left join B is going to give you the item on the left, which is A, all of the records in A and only those in B where they match. A right join, if I did A right join B, that is going to give me all the records in B and only those in A where it matches. Order matters in left or right joins. So if you're doing a join and you know that you've got some records that aren't showing up because there's no comparator, you want to try an outer join, or this left or right option, to be able to get all of the records from the table you want, and then only the records that match correctly in the other ones. Any non-matching fields are just going to be returned as null. Okay? So that is your joins. They are probably the most powerful part of relational databases. So it's really important that you're comfortable with joins. All right. In the database, there is a data dictionary, which is the part that the DBMS keeps track of all of your metadata. So your information about your database. In this case, we're going to do a lot with the system catalog, and the system catalog will store all of the information about the objects that are in the database, your tables, the columns in them, what data fields are existing in there, what types, what format they're stored in, maybe their domain, their range, whether they're required or optional, so on and so forth, primary key or foreign keys. Keeps track of these options for you so that you can do that. You can run queries against the system database to find this. What is the names of all my tables? Because I want to print out something that says, tell me all the tables. Tell me all the columns that exist in the table. Tell me the data types of those columns. Those exist in metadata, which is included in your data dictionary. The one we're going to use is the system data dictionary. So we can do select star from system and go from that. So it gives you some options there. When you are building your database, you want to try to avoid homonyms and synonyms, words that sound the same or words that mean the same but have two different spellings, just because it's going to cause confusion in your data fields to have multiple things in there. If you had car and auto or car and vehicle or something like that, those are synonyms. They don't need to be in there. You should be able to find a different word for those. In our relationships, again, relational database, all about relationships. We have a one-to-many relationship. And that's going to be the easiest to implement and maintain. And this is the one you want to try to create every time. You want to try to lead towards always having one-to-many relationships. They're the easiest to put in. They're really easy. You have a primary key in your one side, and you have a foreign key on your many side. It works beautifully. This is how relationship database works, if you can keep that one-to-many relationship going. So when we implement this, we are going to create our painter in this example, our painter table with a primary key of a painter number. And then in our painting table, we are going to have a foreign key that is our painter number. And we're going to be able to do a join between those two tables to allow us to implement that in our queries. Let's talk about other relationship types. All right, in your one-to-one relationship, these exist, but you would like to avoid them as much as possible. They should be pretty rare. If you need to enforce a one-to-one relationship, what you actually have to do is add the primary key from the first table as a foreign key in the second table, then turn around and add the primary key from the secondary table as a foreign key in the first table, so that integrity works both directions to force that one-to-one relationship, which is why we don't like to do them. They should be an optional relationship as opposed to a mandatory. We'll talk about optional and mandatory next chapter. But they should be an optional relationship, because if they weren't optional, you would probably put the data in the same table. It's kind of like the example of if I have a student with a phone number. If there's only one phone number that needs to be stored, then you would have a one-to-one relationship. Why not just add the phone number to the student? If you have multiple phone numbers, now we have a one-to-many, and you're back to being good. If I had a social security number, each student should only have one social security number. I don't need a table of social security numbers. I can just add the social security number as a field in my student table and move on. So in a lot of cases, your one-to-one relationships, those tables, those table attributes or those data fields can be put into the first table. You don't really need a secondary table to hold it if it's a one-to-one. If it's a one-to-many, that gives you something a little bit different. The dreaded M-to-N relationship. As I've said multiple times, you want to avoid this if you can. Sometimes you can't, and that's okay. When you build your relationship, you cannot implement a many-to-many relationship directly. You have to build an internal linking table to connect them, because you can't have that relationship of storing multiple foreign keys on each table. So instead of trying to do something where here's my student and then we're going to store all of the foreign keys of classes that they took, we're going to have an enrollment table. So we have a student in a class, many-to-many relationship. We have to build an enrollment table that will store the primary key from both tables. So the primary key of the student ID, and the primary key of the class ID. Both of those have to be stored in that linking table, that enrollment table, to make this work. Now, by adding that middle linking table, I can have a one-to-many relationship with my student and my enrollment, and I can have a one-to-many relationship with my class and my enrollment. Now I can implement it, but you can't just implement it directly. You have to create that linking table in the middle, which is why we like to avoid them.
One of the basic skills that you want to have in database design is being able to normalize your data. Normalization prevents data redundancy. So the basic concept of normalization simply means, can I move this attribute to a different table without it causing trouble? Can I pull out some information so that I don't have to have data redundancy? There are some people that take the concept of normalization a bit extreme. There are people that make a table of all of the possible states that you may live in, so that we can just pull the state name from a table rather than having the data redundancy of having Montana written 23 times. Sometimes that's useful, sometimes it's not. You need to take into account a couple of different things when you're trying to normalize your data. Use of the proper foreign keys will minimize redundancy. So I can pull it out into separate tables. However, does the elimination of an attribute eliminate any information? Does it actually make it harder? Can I get the information from some other way? And is the cost of the lookup actually worth the savings in the data redundancy? And then how is the data used in normal use? Am I going to have to do a secondary join to join with this table? And am I going to have to do it all the time? And is it going to be cumbersome? If I were to pull out, say, zip codes, a lot of people live in the same zip code when they're working in a company. So we could pull out zip codes and we could say the zip code will give you the city, state, and the zip code. So I've just taken 3 data fields from my customers table and pulled them out into a city, state, zip table where the zip code is the primary key. Now I have to link it back. So I have to make sure I still have the zip code file in my original table. And now every time I want the city and the state, I have to do a join with that table to do it. Is that efficient? Is it necessary? Is it better to just keep city, state, and zip as 3 data fields in your table rather than pulling them out? I don't know. And it'll depend on your system and your workflow and whether or not that's something that you want to do to prevent data redundancy, to prevent bad data errors. If a person puts in the wrong zip code, what if they put in, the wrong zip code and then they put in a different city and it actually is confusing? You can't do your mail correctly, nothing gets sent right. So these are things that you want to think about when you're talking about normalizing your data. We will have a whole chapter on normalization further on. So if this is still a little confusing, that's okay. I promise we'll talk about it again. Normalization is a big topic in database design. And the fun thing about designers of databases is everybody normalizes just a little bit different. Everybody will design their database a little different as far as normalization. So some people will pull out fields that don't need to be pulled out according to other people, and that's okay. Again, personal, whatever you want to do in your database, how do you feel it works? Just because it does take a little bit more query processing, are you okay with that? And is it worth it in the long run, or do you think it's not worth it? So we'll talk about data redundancy and normalization a little further. Another topic that we like to talk about is indexes. When you have a field that is indexed in your table, the data dictionary and the internal DBMS code will be able to create an ordered array of the key values and the row ID values to speed up the lookups. If we're going to be doing a join on our primary keys, we're going to want to have that as an index, because when we do our join, we're going to do where our table A primary key is equal to table B foreign key, whatever the name is. If those are already indexed, it speeds up the query because it doesn't have to relook things up. It's got it in a key value pair that it can use. If you're going to be comparing first and last names and you're going to use those as your on clause for a join, which you can do, then now those fields are going to have to do a string search on every single string that is in there, which is computationally expensive. You don't like to compare strings. They're expensive to compare. You can, and you can do it. When I say expensive, I mean computationally expensive. It takes more processing power to compare and look through a list of strings than it does to look through an ordered list of numbers. So if I have a ordered list or an ordered array of key values, I can just scroll down until I get to the one that matches and I'm done and I'm good. But if I have to compare strings, now it gets a little bit harder. If this is a string you're going to use a lot, you might want to index it. Again, they'll sort it for you, the system will, and it'll allow that lookup a little bit easier. That's why we use indexes. You do not want to index every field. I've talked to some intro programmers that are like, yeah, I'm going to just put indexes on every field. I'm like, that's so not necessary. You don't need to do that. Just put indexes on fields that you think you're going to use for lookups frequently. So on this slide, indexes help you find the information. It can be the primary key, but it's not required. It's just a referential point. Primary keys and foreign keys are often indexed because we usually join on those fields. And then you want to have unique indexes where only one row is associated with it, if that's something that you need frequently. So a terminology unique index is one that only has one row associated with it. Indexes are assigned to a single table, but a single table can have many indexes. See how we did that one-to-many thing again? So each table has its own subset of indexes. So my customer table can be indexed on customer ID, maybe customer last name, maybe customer phone number, if that's something I'm going to use for a lookup. And these are things that we can use for indexes just to make sure that our searches and our queries are run more efficiently. So you can have multiple indexes on a single table, but an index is attached to the table, not to the database as a whole. All right, so Dr. Codd came up with some rules. Not every RDMS uses all of the rules. Not every rule is applicable to every DBMS. But these are some things you want to try to have your DBMS work, and you want to kind of follow the rules as much as you can. I'm not going to go through all of them. It's in the book, obviously, because I copied it out of the book. It just kind of lists the things that we want to make sure we do while we're designing our database. So, for example, view updating. Any view that is theoretically updatable must be updatable through the system. The system must have a way to update a table if that table is updatable, or view in this case, which means that the system must have created some sort of a trigger or some sort of a insert query that you can do against that view if it's updatable. Just a couple of, database must support set level inserts, updates, and deletes, because you want to be able to do an insert, update, or delete as a group. You don't want to have to do every record individually. You might want to have some set operations on that as well. Independence, integrity, distribution. Rule 0, all preceding rules are based on the notion that to be considered relational, the data must use the relational facilities exclusively for management. In other words, you don't want to have a database that's a relational database, but not use the fact that it's relational while you're building your database, because that's kind of silly. So again, these are DBMS rules. They're things that go through and describe what we like to think of as a relational database. If it does these things, it should be a relational database. I know, finally, this was a very long chapter. There was a lot of information here. We are to the end, so I'm going to talk about the summary, things to remember and to really pull out of this. Tables are the way that we build databases. That's kind of self-explanatory. The keys are central, that you really need to have keys, and your primary key or your foreign keys are both really, really important while designing your database and while building your database. Your primary operations, select and join, are the two big ones. Select and join. Everything you do from now on is going to be a select and a join. And then we have the other secondary operations, intersects, unions, differences, products, divisions. Your system catalog holds all the metadata. You can query against the metadata, by the way. You can query against the system catalog. And you can ask the system catalog, give me all the table names that exist. Give me all the schemas that exist. Give me all of the columns that exist in this table. There are times that you want to do that. If you want to say, I want to create a secondary table and I want to use that information of what the previous tables are to keep the record names the same or the field names the same or something, you might want to use those catalog informations, but the metadata is in there, and yes, you can query against it. Most important thing about good design is recognizing your relationships, your one-to-one, your one-to-many, your many-to-many. Again, try to avoid your many-to-manys. not in the conceptual, but in the physical implementation, because you can't do it anyway. So think about it while you're writing your theoretical or your conceptual implementations of your ERs, to understand that when you build your actual database, many-to-manys don't exist. You have to put in that helper table. And if you want to put in the helper table at the conceptual side as well, just to make sure you understand it, all good. I'm good with that. Okay? All right. There's a lot. I didn't do all of them, but there are a lot of assignments for this chapter because I do want you to understand the basics. So the problems 1 through 7 are going to reference the store code databases. I have added the store code databases to the general database in SQL Management Studio. So if you want to view the actual data there while you're working on your assignments 1 through 7, feel free. You're going to use either Lucidchart or Draw.io to create your ERs and your diagrams. And then just go ahead and paste those into your submission file, or you can always submit them as a secondary file, like a PDF. If you want to download it as a PDF, go ahead and do that. But if you want to use the snipping tool and go ahead and snip out the image like we talked about in the meeting, you can do that as well. So 1 through 7 from the homework. So after 7, I jumped to 24. I figured 8 through 23 was kind of redundant, and 24 through 31 was the hard one. So I kind of gave you the easy one and the hard one. We'll see how that goes. If you really want to do the medium ones in the middle, you're welcome to. If you're excited and you want to go play, feel free. But I do want you to do the homework problems 24 through 31. These use the airline, so the aviation company. And there's a couple of different questions, not only on your ERD, build this, build your crow's foot, understand this. So I just posted on here the actual tables as they're printed in the book. Again, they're in your SQL Server Management Studio as well. I have not built a design in SQL Server Management Studio for you to just copy and paste that, because the point is for you to build it. But I do want you to see this project, and I want you to think about this aviation company in the sense of, what is the company? What are their business rules? What did they do to build this? This one's kind of a weird one because they've got pilots and co-pilots, and so it adds a little bit of confusion. And this is what happens in the real world. You have things like manager and assistant manager. So I can't just have a store with a manager, because what if there's 2 assistant managers? What if there's 3? How do I handle that? Same concept with this one. You've got a pilot and a co-pilot, but you're not required to have a co-pilot, but you might. And then the hours is going to be related to both of those, and we're going to do some calculations. It's going to be fun. All right. When you are finished with chapter 3, go ahead and go do 4, and then we'll do chapter 7.4 through 7.8 as another video on top of that. Have fun. Remember, our team meeting is Tuesdays at 9 a.m. So if you have questions on this, please just look at it ahead of time so that if you have questions, you can bring them to the team meeting. Otherwise, you can always find me on Teams. Have a fabulous week.